In the previous video we defined the electric potential energy as the charge times the electric field times the position, right? And this is if the electric field is constant, but actually the differential of electric field of potential electric energy is going to be equal to the integral of QE dr, right? And then we can extract Q or whatever. But well, more important than that, well, this is if Q is constant, right? So more important than that, than the electric potential energy, is, for instance, this quantity. And this quantity is going to be defined as the electric potential, and we define it as V. The electric potential is then the integral of E dr evaluated in a certain point. So for instance, if I have a source of electric field, let's suppose it's a positive infinite plate or whatever, which is exerting an electric field towards the outside, since this is positive, well, if I define, for instance, a point in space, this point in space, well, this point in space will have, for instance, something that is a potential. There is no charge there, and this has a potential, right? And then we can actually state this is not depending on the charge we're evaluating here, but only in the distribution. And that's the difference between potential and electric potential energy. The potential does not depend on a charge there. It's only dependent on the source of electric field and the space. So we can define this electric potential as well as the energy over the charge we're evaluating. So this has, for instance, some units that are joules per coulomb. And these joules per coulomb are called volt. Or we can call the potential, we can call it voltage. Now voltage, for instance, voltage, well, that is, for instance, a change in electric potential, such that if I have here the source of electric field, and then I am going to evaluate, for instance, a point here and a point there, well, this has a potential V1, this has a potential V2, and these two, for instance, have a difference which we call the voltage. So the electric potential is going to be this integral, and if we have, for instance, a point charge, well, the point charge is very easily evaluated as, for instance, kq over r squared dr, and this is going to be equal to, for instance, well, kq over r, there is a minus here from r1 to r2, so that the voltage for a point charge is going to be, for instance, kq over, let's put it like this, 1 over r1 minus 1 over r2. And this is the electric potential due to a point charge. If we have a constant electric field, then, for instance, this is going to be only E times the change in position r, right? Well, but then again, since we define our position 0, r1 as 0, okay, no, so yeah, so this is, for instance, the voltage, right? And this is, for instance, the voltage for constant electric fields. This is for point charges. This is for constant electric field. If not, then you have probably to perform an integral. So, for instance, the electric potential energy is given as Q times V, right? Being V the potential, and work is is going to be a change in potential energy, so we can actually use our conservation of energy as well. And well, B is going to be equal to KQ over R if we have a point charge, or is also, if we have a constant electric field, is going to be E times R, and we need to define our zero, and usually we define our zero in the position of the source. So if I evaluate an electric potential here, right, well, I can actually state, for instance, that this guy is going to be E times R, being R here, the distance, the radial distance from the source to the point I am evaluating.